So
I got stuff in. I was just like, okay, gotta get stuff done because
okay, so this claims it's live. Hey. Okay. I will send this to you on Twitter. It looks like we're going to be a little bit laggy. Okay, so that's why hopefully it's okay. If somebody can put in like, if you can put in like headphones for a minute and just see what it sounds like. Okay. Okay. You.
Testing.
So you can watch this here. It's got a pretty good pickup, so it doesn't do crazy things. Just don't like hit the shit.
Yeah.
So if you get a little bit lower, that's fine, but that's okay.
So
Yeah,
that's what it sounds like.
it is what you sound like.
Okay.
All right. I am now streaming and recording locally.
Okay.
Let Alex say like hi and welcome to EXAG. No, yeah, we have to do all that.
Should I go sit down? Should I go sit down?
You're fine. It's only be like a minute. So you'd like to sit down before First thing is, yes, first thing is, I'm just going to assume the stream is working. And then,
That's a good idea.
Yeah, I don't see how that can possibly go wrong.
Yeah, I'm right here. So I can never break.
Oh yeah, I mean, you know, technology. Hey guys, so we're running a little bit behind, which is kind of, you know, how we do these things. So welcome to EXAG, Experimental AI in Games. This year is our third year of doing this workshop, and it's really intended to be a place for us to come together, try really more experimental applications of AI to either different things in games, so everything from procedural content generation through or straight up new kinds of games. And so this year especially, we saw sort of an influx of a lot more machine learning oriented approaches to this, and the first couple of talks are going to be hitting on that topic in particular. So I think at that point, just so you're all aware, we are streaming. If you don't want to be streamed, please let us know. We'll turn it off. That's not an issue at all. But otherwise, we're going to stream this out so people can catch on it for those who can't make it, including my two co-conspirators, Mike Cook and Antonis Liapis, who you know, decided Europe is a faraway place and didn't want to come. Yeah. So I don't really think we need to really have much more preliminaries than that. There'll be a coffee break after the first couple of talks. So you have a chance to hang out, get to talk to each other, and we'll go from there. So to start, we have Scott Lee presenting a prediction of StarCraft map stuff.
So good morning, everyone, and thanks for coming. As you can tell, my name is Scott, and I'm here today to talk to you about using neural networks to help us design game maps. More specifically, I want to talk about using a data-driven approach to procedural content generation, specifically in StarCraft 2 maps. Now, there's been a lot of work already done in the field of procedural content generation, both in research and industry. In research, we see tools like Robotsson and Sentient Sketchbook that help designers design maps and levels for games. And in industry, we have PCG being used to create levels for players to enjoy. Usually, when it's done well, it does great in extending the lifespan of a game and keeping the content fresh. However, we run into this problem when we talk about PCG and making levels and designing levels. and that is evaluation. It's really, really hard to tell what makes a map or a level good. We have these abstract concepts of things like balance or fun or aesthetic, but when we try to quantify those things, it's difficult to slap a number on these. And when we do try to break it down to its basest, most quantifiable forms, we get a very, very complicated and high-dimensional system that, if we're not careful, doesn't necessarily represent the thing that we want to achieve. As an example, here we have these two maps from StarCraft 2, and just by looking at them, it's not necessarily easy to tell which one is balanced or fun. One of these maps was actually removed from the latter because it had lamentable balance, but it's hard to guess just by looking at them which one that is. And this problem carries over pretty directly into procedural content generation. Most procedural content generation up until now has used search-oriented algorithms. They explore this design space to try and find a map or a level that satisfies some set of constraints or optimizes on some variable that's defined by the designer or user in advance. The problem with that is that in order to optimize or to satisfy constraints, they have to be quantifiable. And to be quantifiable, they have to be concrete. And so a user can't necessarily tell a PCG algorithm, make me a balanced map, because a PCG algorithm won't necessarily know what that means, like what variables to look for. And we can see that sort of thing happens in previous work involving StarCraft 1 maps, in which they tried to use a multi-objective optimization to find StarCraft maps, and ultimately ended up getting these maps that do satisfy these constraints, but aren't necessarily, wouldn't necessarily be popular in the competitive player base. And with Mario levels, we see this work involving optimizing on a certain set of item counts or enemy counts. And you also make levels, but these are very complicated levels that don't necessarily match the design of what we saw in other Super Mario Brothers games. Now, one approach to try and solve this was data-driven PCG. This attempts to use pre-existing levels that have already been made by designers, learning what makes those levels good, and then trying to recreate that design in procedurally generated levels. We see that there was work very recently using video gameplay videos of Super Mario Brothers to observe these maps and generate new ones. And we want to see if this approach follows into StarCraft 2. Now, for those of you who may be unfamiliar or don't necessarily remember what StarCraft 2 is, it's a real-time strategy game in which 2 or more players attempt to collect resources, use those resources to build armies, and use those armies to destroy the other player's army. It's an incredibly fast-paced game with a lot of strategy, but most of that strategy is rooted within the map design itself. What the map size, the map shape, and the way its geography is can actually very strongly determine how a player is expected to play this game at any given time. So what we wanted to do was we wanted to train a neural network, see if we could train a neural network to learn what makes StarCraft 2 maps good. And to do that, we downloaded the set of maps that came with the StarCraft 2 game, that numbers to about 147 designer-made maps, and then extracted the height map and the resource sets from those and turned those into images. Now, the height map is represented by a byte matrix at the lowest level, and so it made a lot of sense to just reconstruct it as if it were an image. And that actually lends itself very, very well to neural networks that specialize in image processing, such as convolutional neural networks. However, you do have to downsample these to make them slightly smaller, because at their full size, they are roughly 200 by 200 on average, and that makes it so that your neural network is going to be roughly 50, 60 gigabytes in size, and we don't have that kind of memory. So for this project, we decided to train 3 different neural networks. A very simple neural network, fully connected, single layer, nothing special. One shallow convolutional neural network that is just a single convolution hidden layer, and a deep network that took a few more layers of convolution to try and learn perhaps the more intricate patterns within these StarCraft maps. And what we ended up getting was something that isn't really all that bad. What you see here is actually one of the predictions that our 3 networks made. On the left is the height map we inputs. In the middle here is the downsampled version of the expected mineral placements, what Blizzard intended for their map. And on the right, you can see the outputs of the neural networks. In the white are the suggestions as is, and in the red and blue are the suggestions overlaid on top of the expectations. The blue represents the neural network suggestions, the red represents the expectations. Yes?
When you say prediction, what's the
The input is the height map on the left right here. So we input the height map into the neural network and then had it output this resource map. And so the areas of white represent points of overlap. As you can see, they're pretty close to one another in overall shape. They are missing a couple of points in the middle, but they don't necessarily have a lot of direct overlap, even though they are close. Now, to do this, we had to do a decent amount of post-processing. Because neural networks don't necessarily output clean binary 0 and 1s, it actually outputs a distribution of values between 0 and 1, based on how confident a neural network is on where these minerals go. And so at first, we started by filtering out the lower confidence value, the lower confidence areas. We did this by removing the 95th, yes, the top 95th percentile of minerals were retained, and everything else was reduced to 0. And then we performed a clustering operation. So minerals in StarCraft 2 never exist alone. They're always in sets. And so we can remove these sort of scattered bits because we can attribute that to just very high value noise. And what we get is this sort of cleaner looking thing that you see on the right here. Now, the one problem that our networks ran into was overfitting. I attribute this to the scarcity of data mostly, but it is a problem, and I think it needs to be addressed. So what you see here is the mean squared error for our neural net performances. In the red is the deep convolutional neural nets, in the green is the shallow convolution, and in the blue is the simple non-convolutional network. The dotted line represents the error on the training sets, and the solid line represents the error on the validation set. Now, the point at which the training and validation set errors diverge is where we begin to see overfitting. Your network does very, very well on things that it's being trained on, but it begins to lose a lot of performance in the things that it's being tested on. And what we see here is that the deep convolutional neural network actually overfits much, much more severely than the shallow convolutional nets. It seems that a neural network doesn't necessarily have to be that deep to do reasonably well in this task. And the simple neural network actually does reasonably well. It doesn't overfit that severely, even if it never does quite as well as the convolutional networks on the training sets. The one thing, though, is that the mean squared error criterion basically just takes the expectation and the prediction, overlays them, and subtracts them, meaning that even if they're close, if they're not directly on top of the expectation, it's going to penalize it. And that's not necessarily what we want, because we do want them to be reasonably close. That's still an acceptable result. And so these errors might actually not necessarily be indicative of a badly performing network. We can see here, these three are suggestions given by the networks after the overfitting happens, long after the overfitting. And you can see they're still reasonably close, but the error is registered as very large because they don't actually overlap at any of the points. They just come very close to all of the points. So yes, overfitting is a problem. 147 maps isn't that many necessarily, but at the same time, they don't really perform as badly as the numbers would imply. Yes?
Depending on the height map, would be slightly off, be a lot bigger deal. Maybe up in a lot higher area.
So yes, if the mineral suggestion is on a different height point than the expected, yes, it would be a problem. At the same time, just as a design pattern in StarCraft 2 maps, minerals are placed near but not really at the edge. So if they're reasonably close, unless they're like too far off, you can reasonably expect that they'll be on the same plateau, so to speak, just because there is that buffer space around the minerals. Yes?
So you just use height maps? You didn't use walls?
No, so we simply extracted the height maps from the map files. We could have used walls, but that would have added, I think, another layer of complication to what the network was trying to learn. And I was under the impression that the height map would have been adequate to tell us what we wanted to know. Now, as we can see, these results, I think they are promising. And neural networks specifically give us a lot of unique options that other algorithms don't necessarily. One of the big things is that we can actually train neural networks on whatever set of maps we want. So instead of training it just on Blizzard maps, if a designer, say, liked a specific kind of particularly large map, he or she can download his favorite maps and train a neural network on those and replicate that design process instead of, say, Blizzard's design process or whatever set of data that we chose to train it on. And another big thing is that because neural networks do output as this distribution that we do filter out, we can actually change how strict the filtering process is to get more or less resource suggestions. Now, this would be something in line with a sentient sketchbook type of tool, where as they make the map, it would suggest minerals, and then if the designer wants more or less minerals on their map, they can move a slider back and forth. And so you can see here, on the left in yellow is the original, the one that we output under normal circumstances. And then as you go from left to right, we can actually change whether or not it's just less or more. On the left, you have these very few sparse mineral distributions that the neural network is absolutely sure on. These are the top 1% of mineral suggestions. Let's say a designer wants more mineral suggestions. You know, they're confident in what they're making. They want to just go through them themselves, and they just want the entire set of what they could make. Then you lessen the restrictions, and you get a lot more, maybe a little bit out there mineral suggestions for the designer to work with. And so for future work, I want to talk about some suggestions in generating the height maps themselves, going past the mineral resource suggestions. Now, the idea behind this is a sort of image autocomplete, which we see does exist in graphics already. But in game design, it's a lot more complicated because there is a certain design implication behind it. You want to sort of read what the designer is doing, find the pattern that they're trying to create, and then propagate that pattern across the rest of the map. A tool like this would be predominantly geared toward designers who maybe have an idea of what they want to make. They have half the map that they're very proud of, but don't necessarily know how to add those finishing touches. You would create most of the map, and then the neural network, using what it knows about neural networks already, using what it knows about maps already, would look at what you've made and try and finish it for you, would be the idea. So just as a brief summary, we wanted to use neural networks on StarCraft 2 maps to see if they could tell us where minerals should go given a height map. And they do have some initially promising results. They don't look bad, but they do definitely overfit. We see that in the numbers, and it is a bit of a problem. And that stems mostly from data scarcity because 150 maps really isn't that many given the complexity of the data problem. And our error measure wasn't necessarily what we wanted it to be. It doesn't fully represent a closeness metric. It more represents this exact right or wrong metric. But at the same time, a data-driven approach does give us a lot more options and customization on how we want this data to be presented. Users have the option of training a neural network on the data that they like. And if they want more or less of it, they have the option to do so because of the way neural networks operate. And that's my presentation. Thank you so much for listening. Yes.
In terms of the error measure, there are metrics you can use that are more robust with respect to like small translations and stuff like that. You try, doing a Gaussian blurring before you subtract, or using a distance transform, something like that.
No, I haven't, but that is a really good idea.
That might make that might give you a way of quantifying your intuition that the performance is better than the data sets.
So you mentioned data scarcity being an issue. Did you consider using any of the community-created maps?
So with community-created maps, we did consider that at one point, but for this project, because we wanted to be absolutely sure that the maps we were putting in were consistent in design and of quality, community-created maps, while they are vetted very thoroughly, but we just want to be absolutely sure for this first time. But we do want to expand into the community-created maps just to get a lot more of that data, because I do think it would be very useful.
Sort of on that note, did you consider sort of artificial ways of inflating your corpus size, like doing rotations or like reflections or something like that? Don't really change the underlying properties of the map, but sort of give you a more robust corpus.
Yes, I did neglect to mention that when I was talking. We did use rotation methodology. We rotated by 90 degrees all of the maps to give that robustness. The problem with rotating 180 and 270 degrees is because of the functional symmetry of StarCraft 2 maps. If you rotate it by 180 degrees, you risk creating duplicates within the training sets, which aren't necessarily helpful. And if it bleeds into your validation set, it's a pretty big problem because then you have leaking. Yes?
We think if with one vertical operation for the neural network output to generate some useful cluster clustering.
I'm sorry, I didn't hear that. Can you speak up a little bit?
Clustering method to remove the noise and generate some resources for what you run. And
Oh.
if you use some mathematical operation in this processing, maybe find better application for the resources.
Okay, just to make sure I know what you're asking, you're basically talking about integrating the clustering and the noise filtering within the neural network itself, yes? That is an idea. The one thing, so my concern there would be inserting, so those are the functionalities that do add a lot of customization ability to working with the output of the neural network. By creating it in this raw form, we can manipulate it a lot more freely than if we put it in at the end of the neural network. That's my opinion, but yeah, that is a good point, and it's definitely worth looking into. Yes.
How did your error on mineral placement vary with thresholds of the
Oh. So no, this was just on the base system. So we didn't actually, this is using the base fuzzy noisy thing and comparing it against the outputs, this error right here. If we do it by 0 and 1, that creates, it's a binary comparison, and it could work. I think it could work. It would be somewhat more difficult just because such a, to think a little bit here. Yeah, I think that could work. I think it's worth trying, but for this one, we only compared it to the raw output of the neural network.
Can you go to the slide of your neural network architecture?
Sure. Yes.
Did you consider, I mean, since you saw that there was such drastic overfitting, did you consider like doing things like regularization or dropout or things like that that are like, you know, designed to combat overfitting?
We tried a couple. We had a dropout layer at one point, but I think because of the scarcity of data, it was dropping out important things, and so it wasn't necessarily performing better. The overfitting was less severe, yes, but it also wasn't performing as well, just as output, as general outputs. I think with more data, it would be much more robust to that information loss that you would get from dropout, and it would be a good idea at that point. Yes.
So your network outputs, I guess at the top level, a single real number, like sort of the probability of there being a resource there for each pixel, that's what it is?
It kind of is, because so with the input, if it's not a mineral, it's 0, and if there is a mineral, it's 1. That's the input of the training. So when it does output, yeah, it will pretty much be sort of the confidence, how confident the neural network is that our resource is there.
In that case, the problem sort of resembles in graphics when people try to do foreground background segmentation, where you really want like a single bit boolean as a foreground background, in which case the typical thing would be using conditional random fields to say, like, solve for the configuration of these bits that locally it agrees with the continuous value from the prediction, but also exploits knowledge that foreground pixels are often connected to foreground pixels and so on. So it's another model you train on top of it, but it's that conditional random field, so this adaptive piece that goes from sort of a field of reals to those crisp bits on top.
It's a really interesting idea. I will definitely look into that.
One thing that you said was that like you didn't want to do the full size because that would lead to like a really large model. But people doing image stuff like do the full number of pixels, like do pixels of that size and don't have models that large because they're not using a fully connected last year. They're using like deconvolutional and unpooling methods. Did you consider those, or is that just sort of future work?
That's a future work idea, I think.
All right, let's thank our speaker. So, as we now, of course, continue along the trajectory of completely linked topics, we'll move on to predicting draft picks in Defense of the Ancients. As soon as that starts working. In the meantime, I will just kind of fill spare space here. Yeah. So if there are questions about the evening activities today is the day that we're going to mostly focus on doing any tutorials. So if you wanted to do a tutorial, either one you submitted or if you have stuff you'd like to do one on, today is the best day to do that. We'll also be doing some of the sort of hacking in parallel Tomorrow will mostly emphasize the demos in the evening chunk of those sessions. So tomorrow will be the time where if you've thrown something together today, or you have other stuff that you wanted to show off and start getting some community visibility with, get some feedback, that's going to be your great opportunity to do that.
Is anyone good at this? I don't know. But yeah.
Yeah, I'm just impressed.
How do I? Why do I not mirror? Do I need to?
Maybe you're just plugging the projector. Maybe hit the built-in display to try to mirror it.
Sorry, what?
Oh, no, that didn't work.
Turn it off. Yep. Apply, I think, before it doesn't.
Apply?
Apply to to that.
Oh, man, I'm good.
That's enormous.
You only need half your screen, right?
Yeah.
Why would you use it for slides?
Right. No, it does not. Okay.
That's
I can also just put the talk on someone else's computer. Or...
Switch resolution to 4:3.
Yeah. Oh. Come on. Click the little pink one.
This one?
Yeah, there you go. Now apply. No, whoa. There we go. Apply.
Apply.
Ooh. It's beautiful.
It should work. It's kind of like the right resolutions.
Except it's not. Oh, it's still not showing the talk. Can I just borrow someone else's computer that might actually work? Or is that okay? Or
Yeah. Volunteer. Whoever's fastest. Someone's on the draw.
Right? Sure. I just have on USB drives. So worry. This one has so. It also inspires.
Gotta get some adware on there.
only some adware?
yeah, PDF. For documents.
It's a document.
Okay, this is not gonna work.
Does the stream crash or anything?
So you don't need the person buttons.
I don't know. No one's yelling at me yet. So
It should be fine.
It must be
I should
fine.
have it plugged in, so what's going on?
Where you touch that?
This is usually it's a good idea.
leave it for video.
This is the one we use.
Yeah.
I like
Should be.
Are you watching your stream?
Do they have?
No, I don't have a laptop.
I will watch your stream.
Thank you.
Oh, yeah.
You got
Order of operations.
Yep. Yeah, it's order of
I'm hoping
operations.
people will start like tweeting.
I hit that yesterday trying to do a talk where it was like, next.
All of you
Talks.
private photos.
And then if you want.
Screen.
We did it.
All right.
Oh, we're living the dream, people. We're living the dream. Okay. Yeah.
All right.
And done. Okay. Hello, my name is Adam Summerville, and today I'm going to be discussing draft analysis of the ancient, predicting draft picks in DotA 2 using machine learning. I'm at the Expressive Intelligence Studio at UC Santa Cruz, but this work was done in conjunction with Mike Cook, who sadly cannot be here, and Ben Steenhuisen, who I think that's his name, or that's how you pronounce it. I've only read it, so sorry, Ben, if you're watching this right now and I massacred your name, but okay, DotA. So for those of you who don't know DotA, it started as a Warcraft 3 mod, or at least the variant that became DotA 2 started as a Warcraft 3 mod. I'm pretty sure that Alex started this as like the Blizzard section because of corporate self-interest, but we're not going to go talk about that. But anyway, so started as a Warcraft 3 mod, keeps the trappings of real-time strategy games of, you have a cursor, you click on things, but drops the, you have a base, you're building, you're controlling an army, and each person, each player only controls one character, or in the case of some special characters, they might have multiple such things, but we're not going to talk about that. But for the most part, controlling one character, that hero has sort of standard RPG-ish stats, and they gain experience, and they level up, and then the player gets to unlock new abilities. They get gold and can buy loot. So started as a Warcraft 3 mod. Valve bought the rights and created Dota 2. And that's what we're going to be really talking about today. It's a big deal, 43 million monthly active users, and there's a large premier tournament every year known as the International. And this last year had a $20 million payout, so a lot of people playing it, a lot of money. And so we're going to first just give you a little overview of how the game is played, and then go into the drafting. So this is the Dota 2 map. There's two sides, two teams. There's in the bottom left corner the Radiant, in the upper right the Dire. Each team is composed of 5 players. They fight along in conjunction with computer-controlled entities that go along these lanes, and the goal is to destroy the other team's base. And to do this, you pick one of 112 different heroes, seen here nicely color-coded, that each have their own special abilities and unique traits. And so the main mode that is done for the pro play, there's a lot of different modes of way of playing, is drafting, wherein there's a sort of special metagame on top of the game here with the map and etc., where people go through and pick and ban before the game ever starts, and that's what we're going to be analyzing today. So there's a lot of different reasons why we might care to do this. One is beginner assistance. Like, there's 112 characters. It's a pretty steep cliff for people to start to try to learn, particularly if they want to start getting into drafting. So one might be to offer up suggestions of what heroes it thinks might be good for the player to take based off of the preceding history of the draft. Another is casting. There's a lot of people playing, there's a lot of people watching the game, and casting is a big deal, but all the stats work that is already done is just like there's a very limited number of people. There's a whole wealth of data, all the data is available, but it's really hard to get at interesting things from the data and really bring it to the surface. And so if we could help smaller casters and smaller teams cast better, that might be an interesting thing. Create an AI as like the stats guy. And another one is just Dota 2 itself. There's a lot of sort of nice things about Dota 2. One is that it's it's popular. There's good visibility for research, and also just lots of data is being created. It's not like we're working from a small data set. We have lots of data being constantly created. And the drafting in Dota is interesting because it's easily available. It's all publicly available. Unlike say like Magic the Gathering, which has a very important drafting is very important to that as well, or to one mode of that as well. But it's opaque, or say something like Heroes of the Storm or something, where that drafting data would be unavailable to players because it's behind some sort of corporate wall. Another is that the drafting is very strategic, unlike something like Counter-Strike Go, where there is like people doing loadouts and stuff, but there's no real counterplay, there's no like interesting analysis. It's done in 20 seconds. People don't really care to talk about it for a really long time. And then, the people doing the draft are actually active in the play, which we just think makes it a little bit more interesting than something like fantasy football. So first I'm going to go over drafting, then the machine learning techniques we used, give the results, and conclude. So, as I said, 112 heroes, each team picks 5, each team bans 5, and each hero can fulfill a number of roles, which will go into why a player might want to draft them. That might be just like the raw power of the characters. Just there's some character that's just much better than the others. Is there some synergy on your team that you're trying to create a combo that these two heroes will work really well together? Are you trying to counter the opposing team's strategy? And simply just player preference. Do you practice with one hero? Is that the hero that you're familiar with? So there's a lot of different reasons that might go into a ban. Now, so there's 112 heroes. We might imagine, well, maybe there's just like 10 that are good and are always going to be picked, or 20. But at the most recent, the 2015 International, 93% of the heroes were chosen either to be banned or picked at some point during the tournament. So, it's a very deep roster. We think this is an interesting problem. So here's the draft. It's a series of alternating bans and picks. There's the first ban phase where it starts with team 1, alternating pick, bans. Pick phase 1, team 1 gets the first pick, team 2 gets the next 2, back to team 1. Then another alternating ban phase, another alternating pick phase, another alternating ban phase, and finally reverses so that team 2 gets sort of the final word. Team 1 gets the first word, team 2 gets the final word. This is the most recent version of the draft order. It was actually originally that team 1 had the final pick, but it was determined that that sort of final word was strategically important. So there's some sort of choice and some balancing of the ban there. Okay, so that's the draft, and now we're going to talk about what we sort of want to compare against, which is human predictions. There's human casters. They're making predictions. What are they actually saying? So one such thing might be that Merlini, a caster, predicts that EG, a team, is going to, during any of the pick phases, pick Dazzle. So what is Merlini actually saying here? Is this one prediction? He said one statement. Is it either right or wrong? But that's sort of not exactly what the machine learning algorithm is going to do. Is that actually 5 predictions? Can he only be right once and is guaranteed to be wrong at least 4 times, or is he going to be up to 5 times? Is it pick 1 was it Dazzle, pick 2 was it Dazzle, pick 3, etc. So these are 2 different ways of sort of slicing this human data. And then finally, what about if the human doesn't make a prediction? Casters aren't always predicting every single ban or pick. Do they get a free ride on that? We don't let the machine learning algorithm get a free ride on that. Like, it always has to make a prediction, and it's either right or wrong. Does the human get a free ride on it? Is it just like, so say the second ban, if they didn't say anything, is that just automatically wrong? Is it automatically right? This is another thing that we're going to consider. And so we have sort of 3 separate modes that we're going to consider the human data. One is the lenient, where each prediction is a single unit, no matter how many choices it actually encompasses. We have the strict, where each prediction encompasses all the possible choices that are taken by that. So, for instance, if Team A will pick Dazzle in phase 1, that's actually 2 predictions because there are 2 possible times they could pick. If Team A will ban Dazzle or Doom in phase 1, that's 4 predictions. You can just multiply these out. So, and then finally, the all possible, which is that there are 20 predictions per draft, and not make a prediction is equivalent to a null prediction of I don't know, and that's just automatically going to be wrong. That might not necessarily be fair to the humans since they didn't know that they were going to be graded on this scale. But so we think that true human performance is probably somewhere between strict and all possible. We tried to run an experiment, didn't get any casters to take in time. So just sort of temper it that it'll be probably somewhere between those 2 values. Okay. So that's the draft. That's what we're going to be comparing about. How are we going to actually be doing it? So the first one we chose was Bayes networks. Bayes networks are a graphical model for representing conditional probability distributions. The simplest would be that we're trying to predict hero chosen. So it'll give us some probability of what hero it thinks will be chosen. And we can do this based off of other random variables. So what choice number? So if it's choice number 1, that's ban 1. If it's choice number 5, that's pick 1. And then, a whole host of other things, like what type of choice was it? Was it a ban? Was it a pick? What was the previous choice? We think that, the history might be important, which I'll get into a little bit further on. And then finally, which team was doing it? Is there some strong dependence that team 1 is always going to pick Doom or Dazzle or what have you? And so we considered 3 models. We have the nullogram model, which is just always going to predict the single most likely hero. It's the stupidest possible model, but we wanted to have a really stupid baseline to compare against to see how well these smarter things actually did. The next one would be based off of choice number, and then the full model. So right, we have the DotA draft as a sequence. you know, at least this is one way of slicing the data where it's, you know, we have some history. Pick one, or band 1 was Clockwork, band 2 was Batrider. What do we think the next thing is going to be? You know, we'd hope that the machine learning system would be smart and would say, well, I know it's not going to be those two because I've seen those before. It can't possibly be those. They've been banned. You know, we would hope that the system could learn that. And so to do that, we used what is, you know, sort of the current state of the art in sequence analysis, which is long short-term memory recurrent neural networks. Here's the long short-term memory cell, which is the sort of basis of the LSTM, as I'm just going to be referring to it from now on. LSTMs are building off of the building blocks of just standard recurrent neural networks. They have, you know, some extra additional machinery of the output gate, the input gate, and the forget gate. At least in my mind, the core contribution is that the recurrent edge, instead of just being part of the output, that the recurrent memory portion of it goes through a summation and not a product. This allows the error to decay at a much, the memory to decay at a much lower rate than if it was just multiplicative. So if you multiply something a bunch of times, it's a power, it shrinks to 0 really quick since these things are clamped between 0 and 1. And that it has the forget gate, which causes this memory to decay at the rate of forgetting, which is what you want, not necessarily at the rate of the output. So an LSTM is a bunch of those cells densely connected, and then, you know, we have the input, which is what is known as a one-hot encoding, where it will be, you know, each different character will have some entry in the input, and it's either 1 if that hero was selected, 0 if that hero wasn't selected. And then the final layer coming out will have what's known as a softmax, where it takes the values, exponentiates them, and sums that, and then divides by that. So what you get is, by exponentiating, you make sure that everything's greater than 0, and by taking the sum, and dividing by it, you guarantee that it is now between 0 and 1, which is what we want from a probability distribution. So it gives you a probability distribution over which heroes it thinks is going to be the most likely next prediction. And this is, you know, you unroll this during training time to get for some amount of time steps in the past. So it'll give us the probability of choice of I given the preceding history. And so for this work, we used 4 layers of 512 cells with aggressive dropout to try to avoid overfitting. Now, we didn't take just the straight hero, 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 hero. We did include some other information, but, you know, so we have this as the sort of simplest possible sequence, but we also included other information such as, like, was that pick a ban? Which team was doing it, and which at what point in the draft was it? And so we have this sort of meta information as well in our sequence. Okay, results. This work was done on DotA 2 patch 6.85. We looked at 1,500 different pro games, all of the pro games during this patch, and the human analysis was from 23 games from this. We used tenfold cross-validation with a held-out test set. Now, we see that the simplest, the baseline, is 4.93%. Now, if you're doing the math, the most likely one, there's 20 picks. The best they could possibly do is 5%. So we see that the most likely hero was picked nearly every single time. So by just being stupid and always saying it's going to be Doom, it gets it 4.93% of the time. So we see that by including some other information, like where you are in the draft, we go up to about 10%. So we're, you know, looking at, you know, 2 picks right per draft. It's not great, but, you know, as we go on, it gets a little bit better. The LSTM is the best. It is statistically significantly the best, although, you know, it's maybe in real terms not terribly much the best. But, you know, we're getting 2 to 2.5 at the right, you know, per time. So it's not ideal, but you know, we want to see how does this actually compare to humans doing it. So again, if you remember, we have the human lenient, which is that each time they say something, they can either just be right or wrong, and they get it right 30% of the time. But you know, if you consider it strictly, they're at 13%, which, you know, we see that the LSTM on the eval set is a little bit above that, and on the test set a little bit below. You know, but unfortunately, given the size of the data, we have no idea if this is actually statistically different or not. But we see that the LSTM is probably right around the human at this level, but if we give the human the all possible one, they drop down to 6.66%. So again, we think the true human performance is probably somewhere in between here. So, you know, barring, you know, looking at future study, we need to actually see this, but the machine learning is doing sort of roughly human or perhaps slightly superhuman in terms of predicting this. So one thing we wanted to consider was this is only looking at the draft data. It has no knowledge of the game itself. It has no idea which heroes win or lose or what type of heroes they are. And, you know, there's some sort of conventional wisdom about, like, well, given different hero roles, you know, people are going to select different things, like, you know, statements such as they're going to want a support to fill out their team, or they need a carry. You know, these are different types. So support helps out the other members of the team. A carry is a type of hero where they start off maybe a little weaker, but they sort of get stronger at a faster rate, and by the end they can carry the team. So, you know, are these sort of these roles that people tend to think exist, like, do they actually exist, like, in the draft data? Are they borne out? Like, are these heroes truly replaceable according to the draft data? So one such one was mid-lane assassins. These are characters that start out in the mid lane and are very good at taking out other heroes. And so we have Shadow Fiend, Queen of Pain, and Templar Assassin, which would generally be considered to be roughly analogous to each other. And we see that it's not really borne out in the data. Maybe Shadow Fiend and Queen of Pain, you can roughly make that, you know, they're more likely to be taken at the beginning, but not as, you know, we go along in the draft. So this is, you know, number of times they were chosen in the data versus the choice number in the draft. So we see that Templar Assassin, extremely unlikely to be taken at the beginning of the draft, more likely at the end. You know, really these are not analogous to each other, at least in terms of drafting. Maybe in terms of in-game play. I'm going to save questions for you, sorry. And then the other one is off-lane solos. Again, another class of heroes that might be thought to be roughly analogous, and again, really not seem to be the case. So we really think that there's probably a lot more work that needs to be done in terms of looking at, you know, this sort of conventional wisdom. What are, like, things that we actually would want to care about? What are the statistics of these heroes? So to conclude, we looked at 1,500 games from a certain Dota 2 patch. We used multiple machine learning techniques to make predictions and compared those against 3 different measures of human Dota 2 draft prediction prowess. We found that the machine learning models performed near or slightly above human capability, depending on how human capability is defined. And we really want to include, you know, more reasoning about the characters in the future, see what is actually important as the subsets of the characters. So, take any questions now. Thank you.
Yeah, just a clarification question. When you show the choice numbers,
yes.
This was one more back.
Oh, sure. This one?
So when the choice numbers are small, those are banning choices.
Yes.
So I should understand this as people are banning those assassins early.
Yes. Yeah, most likely, yeah, like Shadow Fiend is, you know, in what, 1/5 of the games, or yeah, in 1/5 of the games was, you know, banned as the first ban time. So, yeah. Yeah, this is just, yeah, the whole drafting. So. And as, you know, you could tell that, like, if it would happen in the beginning, it is, you know, just as a function of how that happens, like, much likely, less likely to happen at the end. So we'd expect to see either, you know, sort of, you know, a line going down or a line going up slightly, but.
What about your results?
Yeah.
So, just because I wasn't really clear to me, does that mean that given, so you're at a certain point in the pick history, so you have the whole history of what's been banged and what's been picked.
Yep.
Are you just predicting the next thing that's going to happen?
Yes.
And with 13% accuracy?
Yes. So the next, yeah, so this is not like with the LSTM where there's the meta stuff. Like it's stripping that information out. So it's not like oh, I think the next thing will be a ban. Like it does learn that. It learns that with 100% perfect accuracy. But it learns the structure of that. But it's predicting what the next hero chosen would be.
Yeah, because it's a fixed ban pick sequence, right?
Yeah.
But what I'm saying is, so in the sequence, since all the banning and picking stuff is encoded within the sequence, the only thing you need to predict is champion.
Yes.
Right? So you're saying that the next champion you have a 13% prediction rate?
Yes.
Okay. And how does that look from first to the last?
How does that?
How are you predicting at the beginning? How are you predicting at the end? Because obviously at the end there's less things to choose from.
Yeah, I have that graph is in the paper, I believe. It's actually better at the beginning than it is at the end. So during this patch, it was what people believed was a pretty fixed metagame, and actually the first 4, like if you actually just said during ban phase 1, one of these 4 heroes is going to be picked, it would probably have gotten with like 95% like the first pick was typically either Shadow Fiend or Queen of Pain. Second pick was like 70% of the time was Doom. And so if you see with these ones, everything starts off and then it drops down and then it goes back up. It's because for some reason Doom was always the second pick. Never the first pick, not typically the third or fourth, but almost always the second pick. So there was some sort of structure. So it figured out those things pretty well. Things diverged as it went along, but yeah.
So my follow-up is, so I'm a League of Legends player, and so I'm not sure about DotA, but if you're like the casters in League of Legends, for example, it seems to me like they're more concerned with predicting the eventual team comp rather than the next pick, right? Because there's so many things to be picked. So if you're wrong on the 3rd pick, maybe they'll get them on the 4th pick, right? So did you do any experiments with just predicting total team comp at the end of the game?
We did not do any of total team comp. We did do some of what is the top 3 choices, how right was it? If you give it the top 3, it's right about 50 to 60% of the time. So I don't know. I could look into the full team comp, I'm not even sure. Yeah. Anyway.
When you were encoding all the meta information into your inputs, did you take into account who specifically was picking, what player?
Which? So actually, so this is what's known as captain's mode.
I see.
And so it's actually the team captain is the only one making it. But yeah, we don't have any information about team history or things like that. It's that's obviously information we'd like to consider.
Yeah, I'm just coming from the league as well, and a lot of things that you see there is thinking of, okay, well, is this person going to go for a comfort pick? And I thought that might have been.
Yeah, I mean, there is some of that because it's the captain picking it, but for which member of their team, and so there might be there's definitely team-specific information that's lost that humans have access to and still don't do particularly great, but that if we had it, maybe we would do better. I don't know. But yeah.
Do you think there's a data set, there's a way to control for that kind of thing, or is that just always going to be lost onto the data that's out there?
No, I mean, I think that we could incorporate, future work. It's how do we encode as given team's history. Another thing that we wanted to consider was this was looking at an entire patch and then randomly taking things throughout for that held out test set and stuff. That's not how things work in real life. We considered maybe doing an online mode. Given what we've seen from this patch so far, how has the metagame sort of evolved? We don't have you could go back in time and do the historical pick, but that's not how it typically would work in real life. So that's something we wanted to consider. Another one was, can we incorporate this knowledge and then try to look at draft note or patch notes for a new patch? Because it's sort of fixed for a given patch, what the metagame is going to look like. But can we take the patch notes and try to incorporate that knowledge to be okay, it's day 0. What do we think the draft metagame is going to look like? That's again future work. Sure.
So your evaluation has been focused on prediction accuracy. I guess I was wondering, if you were a naive player and you were just using the outputs of the machine learning to do your picks for you, like, would it have come up with a decent set of picks? You know, any intuition on that? And at some point, like that's what I really care about as a player.
Yeah, I mean, right. I imagine that. So running it in like generation mode would give you like the single most like likely pro draft, like the average pro draft. So it probably would give you a pretty good team, you know, for both sides. It would probably roughly do, you know, the wisdom of the pros, you know, smoothed over each other. So it would probably, I mean, it wouldn't be, you know, specifically tailored to a given player or anything, but it'd probably give you a reasonable team.
When it's wrong, how wrong is it? So is it getting like the wrong kind of role? Is it getting similar characters, or is it just totally off?
So like in the beginning phase, like I said, I guess it's a pretty fixed metagame. Like it knows like, oh, it's gonna be one of these guys.
Sure.
And so it's typically like producing one of those. And so like, how wrong is that? Like, you know, I don't know. Like,
sure.
You know, as it goes along in the draft, like, yeah, I guess it depends on like, right, the L's team is using the categorical cross entropy, so it's trying to minimize how wrong it is in its predictions.
Sure.
But you know, probabilistically, I don't know. Yeah, conventional wisdom how wrong it is.
Okay.
So maybe future analysis.
To follow up on that question regarding applicability to beginners, would it maybe be worthwhile to include whether or not the team, like the picker won or lost them, to say rather than what would a pro be, just what would winners of games be?
Yeah, so yeah, that's possibly one such thing to look at. Is yeah, I mean, like I would say that, right, and there's also a difference between like the pro metagame and the public metagame. I mean, like the public metagame tends to follow the pro metagame, but it can also diverge. Like heroes that are, you know, trash in pro games can dominate in public games because people don't have the proper skills. So, you know, that's one such. You know, I'd say this is probably for people who are, you know, maybe not like beginnerish of beginners, but people of, you know, a little bit into the ranks. They know how to play, but you know, maybe don't have this finer aspect of like the metagame back and forth in the draft down. But yeah. It's, yeah, interesting to consider. Dave?
Yeah,
or we can, I don't know how much time we have or what we're good at.
We're a little bit over, but we can take another question.
Or if there's any.
It's just coffee waiting for everybody outside.
Okay. No, nothing.
Any audio?
Audio is great. Woo! Dave?
Yeah, so my question is kind of related, but I think it would be super interesting to say, okay, so if you had the data of the draft, and then you annotated it with which team won that game,
yeah,
and then more highly weighted in the neural network, the team that won. Maybe
yeah.
you would eliminate some of the control picks and get higher accuracy.
Yeah, it definitely would be interesting to incorporate, also, which team won, or like, given a draft, like, be like, what do you, like, just from the draft data, what do you think the probability of this team winning versus this team is? Would be interesting.
Great, let's thank our speaker. So at this point, it's the coffee break. If you go outside and then out to the left, you'll find the coffee over there. We'll rejoin up about around 11 or so. So go and wake up again.
Just Julian was asking you what schedule link
Unmute.
I think.
Hi, the internet. Oh, so there is a mic. It is right here.
Okay.
It's live. Adam didn't use it, and he seemed to be fine. So it's up to you if you want to use it.
I project very well.
And I think you're cool. I'm gonna go ahead and turn it off then, so we can get.
I mean, if you want to use it, I can. I will just have to like
There's no
adjust
way
my voice.
Unfortunately, there's no way that I can like route through it. So this thing is the actual thing recording.
I see. So I shouldn't be like wandering around over here.
Please don't. But anywhere in this direction is great.
I'm a walker though, so.
Oh jeez.
I might be up here gesticulating.
I'll fix it in post.
Okay. I thought this was live though.
You have a really good editing team.
Yeah.
So is it time to roll, or should I wait a bit?
Wait until people come back in the room and Alex says a little bit like.
I see.
And now we're gonna start again.
Wait for
But
my introduction.
the internet can't hear us now.
Should I go stand in the back and run up to the front?
All three people.
Hey, you gotta start somewhere.
Reverse charge. Charge in rather than charge out.
Yeah.
Yeah,
I think the truism
the modern graphics.
I know. So good.
Things have really advanced in the past 20 years.
But can it really recapture the same magic?
I don't know. Needs to be more polygons.
No.
I think said, excuse me, Julian said, no.
That sounds about right.
Good. All right.
So, hey everybody, welcome back. That's very bright. We're starting back up again. The second session is going to be a lot more focused on the very well-defined topic of models. And we're going to open up with talking about a model of superposed states, which Justus can define far better than I. So, let's welcome him.
Hey everyone, my name is Justus Robertson, and on behalf of myself and Michael Young, I'm here to present a model of superposed states. So here's the outline of my talk. I'm going to begin with an introduction, move through a technical background of the problem, and introduce a example that will be running through the rest of the presentation. Talk about the model of superposed states, and then end with a discussion. So what I'm talking about today applies to interactive narrative, and you can think of interactive narrative as stories that branch and change based on feedback from participants. So some examples of interactive stories are choose your own adventures, text-based adventures, and even some modern AAA games all have stories that branch and change based on feedback from participants. I'm particularly talking about a strong model, a strong story model of interactive storytelling. So one way to encode interactive stories is as a central data structure where all the events and the choices are contained in a single place. So for example, this choose your own adventure can be represented as this tree where the nodes are story content, the pages that the player reads, and the edges are decisions the players can make by paging the different, moving between pages. So it's really tough for a human author to write a branching story. So one thing that people have been doing is creating these intelligent agents called experience managers that automatically create the branching stories. So here is my experience manager, my agent, and how a strong story experience manager controls interaction is it creates this central data structure that encodes the story and how it branches and changes, and uses that to control NPCs in an interactive environment. So first, let's kind of talk about how it generates strong story data structures. So most of these agents are given some input, and the input defines a story world. And generally, the story world consists of characters, objects, locations, and mechanics. And it's also given a set of story constraints. So you can kind of think of the story world as defining a set of trajectories through some simulated space. So over here, that's the kind of the set of possible things that could play out given our story world. And what the story constraints do is say, a human author says, well, of those possible events, these are the ones that are really cool. These are the ones that I want to play out. And then generally what the experience manager does is it chooses one of these trajectories as the one it wants to tell. So the next thing it has to handle is how to have this story play out in an interactive environment where a player can actually take action and make decisions. So it's come up with this really great story that it wants to tell, but now it has to deal with what's called the boundary problem. The boundary problem is we've got some great story to tell where we want the player to move through this red door. But the player, given the simulation rules, can take this alternate course of action. In this case, they can move through the blue door, which would invalidate them moving through the red hallway. So what do we do in this situation? One thing we can do is a process called accommodation. And what accommodation does is it allows the player to move through the blue door and then comes up with a new story that still matches our author constraints. So how this works is, here's our initial story, and it has a red link to represent the player moving through the red door. And then when they choose to move through the blue door, we back up and we check our set of trajectories bounded by our author constraints. And in this case, we have one with a blue link, which represents the player moving through the blue door. So we can choose that, and that both matches the player's action and still reaches or matches the author constraints as well. And through this process, we can build an interactive narrative tree that branches and changes, but also the trajectories through the tree match the author constraints set by the human author at the start of the story. But a problem arises when there's no trajectory in our set bounded by story constraints that matches the thing the player wants to do. So in this case, all the possible stories have the player moving through the red hallway. And at that point, the experience manager won't know what to do. It can't use accommodation. So here is our interactive narrative tree. And at this point, whenever we have a state such that no story exists from that state that matches the author's constraints, we'll have these little dead ends. So we have some paths through the tree reach a goal state, they conform to the author's constraints, and some result in a state such that no story can ever be told that will match the author's constraints. I call those dead ends. So one way to view this process of interactive narrative generation is as an adversarial game. And in the framework that I've just been describing, when you tell a story that matches the author's constraints, you view that as a win for the experience manager. And otherwise, you view it as a loss if you ever reach one of these dead ends that a story can't be told that matches the author's constraints. So then what we kind of have is a game tree where we're trying to hit these states that match the goal states defined by the author. And we want to avoid the states that will result in no series of events being able to be told that will hit those states. So what I'm talking about today is a way we can change this game tree such that we'll hit more winning states. And the way I'm going to do this is incorporating a model of player knowledge into this process such that things that the player doesn't know about, instead of just having one way that the world is, we'll model several simultaneous ways the world could be. So we'll model a collection of states that all match what the player knows about the world. So instead of always having this computer-controlled character at room B, if there's a possible world where it's at room B, room C, or room D, we can then move that computer-controlled character to room D if that's the one that will allow the story to continue. So let's move into the technical background. Let's first look at how we generate these interactive narrative graphs. So I come from a planning background, and this tree is built using a planning problem. And the process of planning is taking a planning problem and coming up with a plan, which is a series of events that match these authorial constraints. So here is one example problem, and there's kind of two or three components of a planning problem. We have an initial state and a goal state, which comprise the problem, and then we have a second piece called the domain, which are the possible action templates that characters can take in the story world to change the state. And remember, I was saying the input defines a story world, which has characters, objects, locations, mechanics, and a set of story constraints. Well, you can kind of think of the initial state of the planning problem as defining characters, objects, and locations. The domain as defining the mechanics, how the world can update and change based on what characters do. And the goal state as kind of the author's constraints. What it does is it says, this is how I want the world to end, but you can use that to define the events that happen along the way to get to the end state. So I'm going to walk through this specific example, which I'll be using for the rest of the presentation. As I was talking with Brent, this is kind of a mashup of a Metal Gear game and the end of the GoldenEye TV show and again, Nintendo 64 game. So the player plays Snake. She's a secret agent trying to foil the plans of Boss, who is the computer-controlled antagonist, and he's trying to align this antenna with a satellite that's up in the sky, and the player is trying to prevent the antenna from turning so he can send data up to the satellite. So over here in our initial state, we have our two main characters, Snake and Boss, and here are my visual representations of them. They may look familiar. Characters can have inventory, so Snake is carrying a PP7, C4, which is an explosive, and a detonator for the C4. We also have Boss, has an inventory, he has a laser rifle, a wire, and a phone. We also have rooms, so they're at the top of a satellite dish in what's known as the antenna cradle, which is the final scene from GoldenEye, like I said. And there's 5 rooms. There's the elevator room, gear room, left and right walkways, and the platform. Here's our antenna cradle. They're right up here at this very top point. They both have a starting location. Snake starts at the elevator, and Boss starts at the gear room. Then we have gears that turn the antenna at the gear room, as well as computer terminals that allow, once synced with the satellite, to information be sent back and forth between the antenna and the satellite. Okay, so that's the initial state. That's the way the world is when we start our story. Then we have things the characters can do in the story world. So characters can move from one location to another. They can shoot other characters if they have a gun. They can make a trap if they have a gun and tripwire. They can set a trap at the place they currently are. They can disable a trap if they're co-located with it. They can use a computer terminal if they're co-located with a computer terminal. They can link their phone to the computer terminal to send information if they are co-located with a used computer terminal. And characters can place C4 on objects, and C4 can be detonated to destroy objects. And finally, we have our goal state, which is what we went through at the end of the story. So our goal state is we want Snake to be alive. We want the player to be alive. We want the Boss, the computer-controlled character, not to be alive. We want the Boss to be at the final room, the platform. We want Snake to have disabled a trap set by the Boss. And we want the gears to have been destroyed so the antenna can't align itself with the satellite. Okay, so there's our planning problem. And from that, we're going to build our branching tree. And how this relates to a plan is a plan for the planning problem is one path from the root of this tree that we're going to build to one of the leaf nodes that represent the goal state, which is our set of authorial constraints. So here's one plan for our tree, one path through our tree that conforms to our author constraints. Let's walk through it real quick. We start off here at our initial state, Boss moves to the right walkway. So characters in this, they have to take turns. So the NPCs get a chance to move, then the player. Boss constructs a trap. The player places C4 on the gears. The Boss sets a trap. The player activates the computer terminal, and she destroys, or the Boss activates the computer terminal. The player destroys the gears. The Boss links his phone. The player removes the trap. They both move to the platform where they have their final confrontation, and the Boss is defeated. Okay, so that's great. We found our path through the tree that we want to happen, but now we have to allow the player to take action, which can move us off our trajectory. So we have to solve the boundary problem. So at this point, it's the player has the C4 and she's at the gear room. And she has several choices. She can place the C4 on the gears. She can move to the right walkway, move to the left walkway. There's some things that I haven't pictured here. So she can also place the C4 on the terminal, activate the computer terminal. I think that's all their options. So the player is only constrained by the simulation action set up by the domain problem. So sometimes they can choose good things, like in this case, say they choose to place the C4 on the gears. That's great. That advances us along a path to the goal state. But maybe later on, instead of choosing to move to the right walkway where they can disable a trap, they choose to move to the left walkway. And at this point, there's no story we can tell because for the author wanted the trap to be disabled. And at this point, there's no way that the player can back up, because these are single direction edges, and get over to the right walkway to disable the trap. So at this point, there's no way for us to tell a story that conforms to the author's constraints. And we're at one of these dead ends, so we're at a losing point for the experience manager. Okay, so now I'm going to talk about the superposed state model. So here's the initial state, and what I'm proposing, or what I've done, is instead of just modeling a single state at every node in the tree, we're going to model a collection of states, a set of states at every node in the tree. The set of states correspond to the set of possible states given a model of what the player knows about the story. So we need three things to make this happen. First, we need a model of player knowledge. Then we need to know how to expand the superposition. Then we need to know how to collapse the superposition. So the model of player knowledge that I'm using isn't too complex. It's just that the player knows everything they're co-located with, and they know that everything that happens in the room that they're in. So in this case, at the start of the game, the player just knows that they're at the elevator room and they know what's in their inventory. The next thing we need to be able to do is expand the superposition. So in this case, the superposition expands every time an NPC can take an unobserved action. There are 4 unobserved actions that the boss can take from the initial state. He can move left, he can make a trap, he can use the terminal, or he can move right. So let's say he moves left. That was unobserved by the player, so that gets added to the set of possible worlds that the player could be in. You could also make a trap, that gets added. Could also use the computer terminal, and the player didn't see that, so that gets added. And you could also move to the right walkway, and that gets added to this collection of states. The next thing we need to be able to do is collapse the superposition. So from each of these states, there's only one thing the player can do to start off with, and that is moving from the elevator room to the gear room. And at this point, the player is going to make one of 3 observations. Either they observe no one at the gear room, which means that the boss either moves to the right or left walkway, or they, nice animation for this, or they observe the boss at the gear room with an activated computer terminal, or they observe the boss at the gear room with a trap. And at this point, the experience manager needs to make a decision about which of these worlds they're going to show the player. So let's say it goes with this one right here, which is still superposition, but it's smaller than the one that we had before. And either of these could be a possible world given what the player knows about, has observed in the world so far. So remember a bit ago, we ran into a situation where if the player moves right, everything works out great because they still have a shot to disable the trap. But if they move left, oh no, we're not going to be able to satisfy this constraint that the player is disabled a trap set by the boss at the end of the story. Well, from the superposition right here, we have an opportunity to satisfy it in both of these directions. So if the player moves to the right walkway, great. There's a possible world where the boss moves to the right walkway, and we can go down that path. But if the player moves to the left walkway, we're still fine. The boss has moved to the left walkway in this possible world, and we can continue on with the story. Okay, discussion. So some nice things about this is it allows us to delay choices about what NPCs are doing as long as they're unobserved until further down the game tree. So basically, NPCs can take every action that's available to them that's unobserved simultaneously, and we can only we get to decide what they actually did later on down in the game tree where we might have more information. And this specifically can be used to solve situations that require after-the-fact knowledge, like the one that I just described to you. Some disadvantages of this approach is that it requires more memory to store sets of states rather than single states at every node. It also requires more time to scroll through each of these states and update them to find their successors rather than just a single one. Really quick, here's a way that we can reduce the memory load it requires to model sets of states rather than single states. So one thing you'll notice is some things about superpositions are different, like the position of the boss. Sometimes he's at the left walkway, sometimes he's at the right walkway, and sometimes he's at the gear room. And also the state of the computer terminal may be on or off. But some things remain the same across all states. For example, the location of the player or the location of the gears. So one way to reduce the memory model is to have a set of true or false literals and just store the set once for all of the superposed states, because they're always going to be the same no matter the individual state, and then have an undetermined set that you keep one copy of for each of the possible configurations. And before I end, I just want to point out that I've been talking about this in an interactive narrative context, but you could also imagine this being applied to game trees that don't represent interactive narratives. For example, the game Stratego, real quick, has an element of incomplete knowledge. So you set up your board state at the start of the game, and so does your opponent. And your opponent can't see the values of your figures, and you can't see the value of your opponent's figures. And then gameplay proceeds kind of like checkers until someone tries to capture an opponent's piece. And at that point, you both reveal the value of your soldier, and the one with the better value wins and takes the opponent's piece. So you can imagine taking this model and applying it to the start state. So I know this is a board game, but imagine this is a game world, so the computer has control over the state of the world. You can model all possible configurations that you could have arranged things in as an initial state, and then decide as you move along not only how to control your pawns as you move around the game board, but also retroactively decide the start state that you started from at the start of the game. And so you get to make two decisions instead of just one. And you might be able to use this to try to allow the computer player to win, or you could do it to allow the player to win, or maybe there's some situation that you want to happen in the middle of the board game to give the player experience with, that you could use this extra manipulation to hit. Yeah, thanks.
So when you're making the decision on how to kind of slice up the, or what to present to the player, do you have a heuristic that you use to determine which
so generally you want to do the one that maximizes your probability of reaching the goal state. And to do that, you probably just need to expand the game tree. But part of the problem is in most game trees, there's a, like in chess, you know the payoffs of the other player. Whereas in this, in an interactive narrative, you may not necessarily know, like the player's payoffs may be less explicit. So there's a couple of things you can do, is maybe if you had some model of what you think the player is going to do, you can plug that in, and then expand the game tree or have a heuristic of how you think that the game tree might be expanded. And then you want to choose the choice, not only for the NPCs as you play the game, but also for how you reveal, how you transition through the superposition that maximizes the probability that you're going to hit a goal. And yeah, I haven't done it either. Yeah.
Do you fear that if you had an interactive game that used this technique, that the people playing it would just get the feeling pretty quickly that no matter what decision I make, it would just kind of work out, so I'm not really making any decisions and that can actually experience the game?
So first, I want to say the way I set up the example problem is there's like these very specific outcome, which is like the villain's defeated, the good guy wins. But imagine that instead it has like a more abstract goal, like maybe there was an interesting character arc, or like you have some more abstract model of what a good series of events to play out. So maybe there really are different changes and things that happen in the story world but what you're ensuring and what the experience manager is pushing towards are that some interesting experience plays out. And that way there might be a wide range of things that could happen, but you're staying within the bounds of what those are that are good in some way. Another thing, and then at the end of that, I would say you might want to try to figure out like at what point the player would notice that you're making a bunch of changes, and you could also try to come up with a model of that and never try to go past the point at which the player would figure out that you're meddling with stuff behind the scenes.
Is there any difference between the superposition and the sort of logical inclusion set?
I'm not sure. I would love to investigate that if someone else has already been thinking about it.
Yeah. I know you put some thought into the memory efficiency of storing the states, like, and it seemed like it was like if say 1 out of 10 of the various different elements of the state were shared, then you get a 10x savings. But in the case of the Stratego board game, the number of states in that initial superposition that I just looked at, Stratego, there
would be a lot.
40 pieces, you have 40 factorial configurations. But improving it by factor 10 doesn't. But what would you do? Because it seems like I like the application to the board game thing and being able to do like an adaptive version. But so even for that simple case, it's like, what do you do about the 40 factorial?
It's a good question. I imagine that there's some smart things you could do, maybe some heuristics, maybe not storing all of them, maybe picking out good ones to store. That's a great question, though. Yeah, and yes, I do agree that that speed up or that efficiency on memory is only going to give you so much before you can't, especially in something like that where it's so huge.
If I can offer one possible solution,
yeah,
it would be switching to symbolic planning, like based on sat plan or graph plan, rather than state-space planning. Then dates don't worry about. It's just sort of representation. I don't know if that's going to work for that.
I would say let's talk more about it. I'd love to talk about it. Sure.
Yeah.
So success for this project means something like you build the system, you do a human subjects experiment, and lead people through the graph in good ways, and people don't feel cheated. Success for sort of us as a community is going to be something more like this kind of technology gets put into Inform 8 or something like that, where people from outside of the EXAG community who are making interactive narratives actually start using this, which of course is a lot of work. How painful do you think it would be for someone to try to do something like that? And how much AI does an author need to know in order to be able to author something like that?
At this point, a lot. I mean, I'm the ideal, or one of you are the ideal authors at this point. And I would say a good first step is one thing I'd like to do is take all this code that I've been developing along with the ideas and put it on GitHub for other people to use. I think that's a good first step at this point. But I do agree that the grand dream would be to have a tool set that maybe not just someone off the street, but a trained designer, like interactive narrative designer, could sit down without necessarily knowing or understanding all the AI components behind it. But I do agree, like I'd love to move more in that direction where there were tool sets available that people could use to take advantage and leverage some of this without necessarily being a researcher themselves.
So sort of following up on what you said like trained designer. So do you think that this would be better for like more experienced designers, or like sort of people who are coming into interactive narrative and wanting to try playing around with it? And I have a follow-up question I can answer.
Well, at this point, like even if you're making interactive stories without AI, it still requires a bunch of you know, a bunch of tools, like you're doing something like Inform 7, which I've messed around with that a little bit. It's not necessarily something that you're going to sit down with and do stuff right. Like it takes some training to do that. So I think it's a big step going just from AI researcher to designer, and then it would be another big step going from designer to just someone off the street understanding how to use the tools and play around with it. It's something like, like in Star Trek, where you walk up to the holodeck and say, hey, I want a Sherlock Holmes story, and it just, you step in.
So since it seems like you're targeting like people who are perhaps experienced, like interacting, have you considered reaching out to some of the people, like particularly some of the people who like have their own tools to do, maybe not this, but have done other things like Emily Short or Andrew Plotkin, anybody like that? Or
at least for me, a good step for me would just be curate all my code and have it available to other people. And then at that point, I can start going, hey, who wants to collaborate and figure stuff out? But if you're interested in collaborating with a project or have some idea, or anyone else is, feel free to talk.
I just say another thing you can think about would be like what would be low-hanging fruit that you could sort of cherry pick and try and into the outside world. You know, maybe there are like simple versions that don't require you to understand scripts playing that are like things that get used a lot. Maybe built into tools.
Seems to apply to what you were telling us about last night for your talk.
Oh,
or are you talking about more of like author idioms?
Author idioms, yeah.
So I was asking, like, since you're proposing a system that increases player systems, like how does that affect the creative owner? Like how much more do authors have to write to maybe account for all these new mistakes that are in your system?
So the idea of creating all this AI backend is to lessen the burden on an author. So without this at all, like maybe you would sit down with something like Inform 7 or maybe even like hypertext, and you go through it and create just a bunch of story branches. So the whole idea of creating these AI techniques is that you can kind of just define this problem file. Like I have a problem file like that creates a text adventure that is where the NPCs are controlled, and maybe even state characteristics are controlled by the AI without the human having to do anything. So the whole idea is to try and reduce the amount of content that the human has to create in order to provide interesting experiences for the player.
Cool. Let's thank our speaker. We can keep
So a lot of interesting questions, of course, about adoption, translation, and I think we're going to see that keep coming up for a lot of this stuff, which is definitely a conversation I hope people have a chance to keep digging into on the side and keep going. The next talk is about whales.
Sort of, not really.
The next talk still falls into the models bucket, only now instead of talking about models of the state of the world, we'll talk about models of bosses. And I will again leave it to our speaker to define what's going on rather than trying to rely on me.
Okay. Sorry for the weird color. I couldn't really find a palette that was working out, but hopefully it's not too hard on your eyes. Okay, so good morning. I'm Kristin. I'm from the School of Interactive Computing at the Georgia Institute of Technology. And I'll be talking about a programming model for boss encounters in 2D action games. This was work that was done in collaboration with Eric Butler at the University of Washington and Alexander Zook, who is running this. So for the next 30 minutes or so, I'd like to talk a little bit about bosses. So many of us have fought, both memorable and extremely frustrating bosses in games. And for the purpose of this work, we're going to focus primarily on climactic combat scenarios that are designed to test some form of player skill or used to gate progression in the game. So often these have some sort of narrative significance. You're doing things like fighting often large antagonists or overcoming difficult puzzles. And we're going to take this a step further and look at a specific domain of these kinds of games where you fight bosses, which are 2D action and adventure games. So these are games like Legend of Zelda: Link to the Past, side-scrolling platformers like Castlevania or Mega Man, or bullet hells like Gradius or Ikaruga. And there's some similarities.
And we're done.
Yeah. And so there are a lot of similarities in these games, such as the fact that these are characterized by real-time movement in a continuous space. Often this movement is planar, depending on the camera perspective. There's also this notion of collision-based attacks with static or dynamic objects. So we have concepts like attack boxes, hit boxes, invincibility frames. And then there's also these behaviors that these bosses have that are often state-based or cycling. So things like stages in a boss fight or repeated behaviors. So you might be wondering why we're looking at these games. Well, I'm going to bring up a question. Why haven't we procedurally generated bosses yet? So we've made procedural content generation work for all kinds of other game content, but no one's really successfully generated bosses. I mean, we've explored things like parameter tuning enemies and that kind of thing, but that's fairly limited. And so, I want to point out that bosses are these complex, state-based, and usually reactive entities. And traditionally, they're implemented in general-purpose programming languages and sort of baked into the architecture of a particular game engine. Which means that unlike something like levels, where there's these universal formats like grids of 2D sprites that are consistent across different kinds of games, there isn't an obvious general model that's shared between different kinds of games representing bosses. So our goal here is to have something that is restrictive enough to generate on, but expressive enough to capture semantics of good boss fights. So in this paper, we present a programming model for boss encounters, and it consists of two parts. So the first captures this idea of behavior. So we use finite state machines to drive the behavior of objects in this space. And then we pair these with component-based systems that expose mechanics like collision detection and expose properties of the game state. And throughout this talk, I'll be illustrating this with a prototype implementation of this model and use it to highlight some parts of our discussion. So very quickly, what I'm going to talk about is some very brief related work that's related to what we're doing. I'll talk about our model and use a running example to talk about it. And then finally, I'll show off some preliminary generation and some future work, and hopefully we'll get a good discussion out of that. So one thing you might be asking is, well, you're proposing a programming model or a language for bosses. Can't you go and use existing game description languages? And it turns out for discrete games where you take turns, there's things like PuzzleScript and Ludi, but these don't capture the kinds of continuous movement and continuous mechanics that we want. For real-time games, there's stuff like the video game description language, but this has only been used for arcade-style 2D games, or stuff like Casanova, which captures these notions of collision and physics, but is much too broad for the kind of stuff and restricted scenarios that we're looking at. So we need a model, and I'm going to go ahead and talk about our model as it looks right now. And to do this, I'm going to, one question you might have is this model should be expressive enough to capture high-quality bosses. So in the paper, we go ahead and we encode some high-quality bosses from existing games. And the example that I'm going to use in this talk is the Moldrum boss from The Legend of Zelda: Link to the Past, which some of you may have played. I personally had nightmares of falling off platforms because of it. So, in the screenshot, the player is this character Link with a sword, and Link goes around fighting bosses like this Moldrum boss, which is a segmented worm show here on the left. And so now, let's see if I can get this to work. I'll just show you a quick clip of this particular fight so you can get an idea of the kind of scenario that we're trying to encode with our model. Or not. Okay, let's get that a little bit. So in this example, the player is entering the boss area. This boss Moldrum basically works by running around and randomly choosing directions every couple of seconds. There's a weak point on the boss's tail that the player can hit with their sword. When they do, the boss curls up into a little ball, and then its speed increases progressively as the fight goes on. And if the player hits the boss, then the player is bounced backwards, and if they're not careful, they can get bounced off the platform and down to the floor below. Okay, so a lot of what I just talked about was talking about the behavior of the boss. So let's start out with how we're representing behavior in our model. So we do this using finite state machines. You're probably all familiar with this. Nodes represent actions that the bosses can take. Edges represent transition predicates that can be taken between actions. So for example, we have nodes that do things like set velocities, have an object chase a target, emit things like projectiles, turn hitboxes on and off. And then we have edges that condition on predicates like evaluate to true after a certain amount of time has passed, or if something collides with something else, or if a damageable hitbox got hit. And so the next question is, well, you have all these behaviors, what are they operating on? And these operate on what we call these component-based systems. So there are these systems, and they expose mechanics and properties of objects. So for example, a physics system has some idea of collisions. It can report when objects collide, and then anything that subscribes to this physics system will also have available to it things like position, velocity, geometric shape. Likewise, we can do something very similar for damage, so that we have a system that reports damage events, and it also exposes notions to objects like health, what team you're on, what kind of damage you can take and receive. And we can augment this with other kinds of systems like an input system that listens for player actions, things like rendering, things like animation. But for the discussion we're having here and in the paper, we only talk about the two on the left. So we're only going to talk about physics and damage. So how do we use these to build finite state machines? Well, here's an example using a physics system. We have a physics system. There's some state vector that's also floating out in space. And so we can create a node that just sets a vector. And the vector that we'll put into this is the velocity of some object. We'll set it to some other target vector. And then we can just build a really simple graph where the velocity gets set. We leave it to the physics system to sort of update it. So its position is changing as a function of the velocity. And then maybe when it collides with something, we'll have it choose a new velocity to pick. And this is just a very simple finite state machine. So how do we apply this to something like the Moldarm boss? So Moldarm, it's this segmented worm. It consists of these physical objects. Each object has a position and some kind of velocity. It also has a geometrical shape, which in this case is a circle. It's pretty easy. And then these objects can also sort of be augmented with these damage properties, like things like, the head can damage the player, the body can also damage the player, and the tail in this case can both damage the player and serves as a weak point that the player can damage. And so then what we do is we write some things where we can subscribe these objects to the system. So in this case, we're making the head an actual physical object. We're setting some things about its damage and its health. And then our system basically takes all of these and exposes them as global declarations that the graph can act on. Please don't worry about the syntax. What's really important here is the semantics of what it's capturing. So what does this actual graph look like? Well, in the video I showed you, Moldarm's movement is driven primarily by the random velocity chosen by its head. So we'll do something like we'll set up a random velocity. And then we'll assign this to the linear velocity. We'll let it just sort of run around and let the physics system update it for a bit. And then eventually, after some amount of time, it'll go ahead and pick a new velocity. So it'll look something like this. So it's very simple. It's going to run off the screen. It'll come back on the screen in a little bit because it's just sort of bouncing around randomly. But this doesn't really capture how this boss actually behaves, because obviously right now the boss is not interacting with the environment at all. So what we can do instead is now we can start having it interact with the environment. So we can set up some edges like, when it collides with something like a wall or the edge of a platform, we just want it to reverse its velocity. And once we do, and then, again, we assign the linear velocity, and once it does that, then we end up with something that looks a little bit like blue. Okay. Okay, so we can have something that sort of bounces around like this. And this is sort of, this sort of looks kind of like the random frenetic behavior we were seeing in the original flight. But in addition, we want it to start interacting with the player, so we can do things like, once the player damages it, we can set its velocity to 0, and then the boss will sort of curl up into a little ball. It'll become invincible for a little bit. And then after a certain period of time, we'll go ahead and increase its speed, set a couple of hitboxes on so that you can hit it again, and then resume picking this random velocity. And so this is just the behavior of the head. We can start adding parts of the body to it. So, Moldarm's body is characterized by these sort of linked appendages that are attached to it, and they all behave very similarly in that they follow the segment in front of it. So we can just have a single node graph where every part of the body and the tail just runs around and chases the target. And when you put it to, and the target in this case might be something like the position of the head. So now what we end up with is a boss that sort of bounces around and looks like this. And so I've omitted the player in here, but hopefully this captures the idea that you have this boss that can sort of randomly around and it'll damage the player. I didn't go into it in this particular example, but you can represent the player as well as the environment using the same representation we used for the boss. So you can have multiple players, different parts of the environment. And in the paper, we also talk about a bunch of other different examples. So Dracula from Castlevania is an example we used to demonstrate how it would work for a side-scrolling game with projectiles. We also talk about Dr. Eggman from the original Sonic. So in summary, I just very quickly described a programming language for, or model for boss encounters in 2D action games. And we want to, and the whole point is we want to generate bosses, but we need an appropriate representation. And specifically, we want this representation to be expressive so that the search space of things that we're generating on has good artifacts in it. So we can encode, we show in our paper, we can encode different high quality bosses, and we can obviously do it with a lot more. But we also want it to be restrictive. So we want to make sure that the bosses we're generating are not overwhelmed with garbage that's completely unplayable. And so for the next part, I'll show you a couple some examples using a demo that I have, and talk about how you might go about generating boss programs and what kind of parameters we have at our disposal to generate with. Oh no. Oh dear. Well, that's awkward. Give me 2 seconds. How is everybody doing today? I'm just going to change the screen size really fast. I was not expecting this to be an issue. Okay, well anyway, you know what? Maybe we'll just try and run it anyway, and maybe it'll be okay. We can see some of it. Or apparently none of it.
Can you make the resolution of the projected thing right? Or is it next? Somebody turned it up really high before, so I think the projector can support higher resolution.
Does anyone, sorry, I didn't expect this to be a... I'm really sorry about this. Oh, of course, everything.
You're about 10 minutes until you hit my record, so good.
Okay, well, thank you for being understanding.
Honestly, somewhat mental.
It's like Jaws.
That is exactly the feeling. It's like, this is a game. It's like, you're stuck the avatar here. It's like, where's the boss?
So can we encode that to take rank as the question?
Well, given that we just saw it, yes.
All right, visible resolution.
Oh my goodness, yes! Okay. All right. Okay. So this is the Holmgård boss that you saw before. The players actually run and I can start whacking things. So yes, it actually works. So here the boss is curling up into a ball. So it's like, so when we think about generation, we can think about what kind of parameters we want to generate and operate on. So I mentioned there are these two parts to the model. There's these finite state machines, and there's all this game states of properties like physics and velocity, and like what kinds of physics objects you spawn. So if I just whack a couple of buttons, we can do things like we can start generating bosses of different size. I'm using the Moldorm example here because Moldorm, is a well-defined boss, and we want something that looks pretty reasonable for this demo. I don't want anything completely unplayable. Or we can do things like fiddle around with the speed, or fiddle around with both. Or do things like change the position of the weak point eventually. Oh, there we go. Okay, yeah. So we can do things like that. Okay. So this is very similar to what we've done before with enemies in games. This is basically parameter tuning, right? And so a lot of this matters and is interesting, but there's also things we can do, like we can start mucking around with the graph. So as I mentioned before, Moldorm's movement is defined by choosing a random velocity. But velocity is a 2D vector. So hypothetically, you could plug any 2D vector that you've got exposed to you into this example. So let's see if it does it. Okay, so here we have this weird example where now Moldorm is teleporting because instead of choosing a random velocity, I'm choosing a random position and I'm adjusting its position instead of its velocity. So, this may look a little bit strange and it's pretty simple, but this, without even changing the graph, all of a sudden we can start getting different behavior. So what if we wanted to start changing the graph? Well, we can try and start changing the graph and maybe something weird will happen. So I have this weird example where that's not it. Okay, so here I just forcibly ripped the part of the random velocity portion of the graph from Moldorm, and now I've attached it to the body segment. So every time the body segments get damaged, it's using the same behavior that Moldorm's head is using. And now we've got something that's completely ridiculous and not necessarily playable, but this brings up the question of, we can get a lot, just by changing very simple things, we can immediately wildly vary from something that's completely playable to something that isn't. And so how do we find good bosses in this space? And that's sort of one of the challenges. Let me just generate some, or try to generate some random bosses here. So now I can just sort of randomly generate some things. I have an example in here that I'm not going to fish for, where this basically turns into a really funny game of whack-a-mole because things start teleporting everywhere. But you'll have to believe me that it's the most hilarious thing that I could generate with this particularly limited space. But yeah, let's go back to the slides. Okay, so I highlighted some of the challenges involved with this, which are, this is really trying to generate bosses is a little bit tricky. And so, the first thing is, well, what kind of approaches would you be used? Like, what generative methods are appropriate? So what we've talked about here is a programming model. So we think that things like grammar-based generative methods would be appropriate for this space. We've used them for levels. How would these same techniques apply to something that we've defined a grammar and semantics for? And the second question comes up, how do we control this generation? So you saw these wildly varying results where I was doing things like swapping positions and velocities. So one thing we're exploring is we have a language, and a language defines a type system. So can we add a type system that enforces well-formed behaviors? So do we distinguish between things like position and velocity? These are both vectors. They're two floating point numbers, but they represent fundamentally different values. One is a position, one is its first derivative. And then finally, there's this question of how do we enforce quality and playability? I sort of picked the parameters that were being used in that particular example, but coming up with what parameters might be valid is still an open question. And one thing that you might want to do is, we have all these techniques for incorporating player performance in automatic parameter tuning and automatic playtesting. Can we incorporate these into this kind of system to sort of explore this parameter space while letting players fight bosses, because that would be really fun. So what do we envision as some of the applications for this kind of thing? Well, if I hadn't alluded to it before, games with procedurally generated bosses would be awesome, and specifically those that would adapt to the player. So can we have a version of something that looks like Shadow of the Colossus, where the entire sequence of bosses is procedurally generated? Or can we have a game like Monster Hunter, where players can take on different classes of weapons and have a progression of bosses that's designed to and tailored to that specific experience or weapon set that they're using? And then there's other things like, we could come up with design tools to help players or developers quickly prototype or explore bosses. As I mentioned before, a lot of times these bosses are sort of baked into particular game architectures and game engines with a small system that was able to, let players of these 2D action kind of games just look at the bosses or like plug their own little players into it to test and explore the space. That might be very helpful. So that's all I have. I'd quickly like to thank my colleagues, Eric and Alex for helping out with this work. This was great, and I'd be happy to field any questions you have. I'll just leave this running, I guess. And the player is currently invincible so that I wouldn't die in the middle of the demo. Okay, yes, I'm going to start on this side.
Yeah. First, maybe just want to say this is great work, really cool, and I think that's going to be really cool stuff coming out of this, especially the building it based on generation of these things. So yeah, really nice. We had some similar things some time ago that never unpublished. We're trying to specifically target the Mega Man boss space and evolving it sense. Never published because it never got to the stage where it was and student finish, which is annoying and trying to stop that. But it's a, but no, it's a, the big problem is like how do you get, how do you make sure they're playable? How do you make sure they're playable? How do you estimate the small change in this interpretation will make it difficult to split a lot? So basically, we could talk later on about then exchange some experience about this.
Yeah.
We basically thought MCPS, because you always think of course, for figuring out the difficulty. The problem is you get some kind of mean difficulty. What you want to make sure is that it's not too unpredictable.
Yeah.
Experience, which is really hard.
Yeah, like a lot of the reasons that we thought of this a lot as a programming language because we wanted to do things like it would be beautiful if a well-formed program in this model was a playable boss, right? Like that is sort of like the ideal, but obviously that's really, really difficult because you've got this parameter space of things to choose from, and then you don't know if these graphs are necessarily valid, right? So you could just generate a bunch of parameters, and the graph will operate on completely different ones, and then nothing will get done.
Right. You could probably get somewhere there, but some kind of balance between how much you restrict it by for purposes of data. And you also want these really surprising things you've never seen before, but it's still playable.
Yeah, but yeah, let's definitely talk. I'd be very interested to hear about kind of what that you did. Yes?
So the usual thing to do in industry practice would be to represent the state machine as a behavior tree. Because then like the transformations on everyone's net, all that stuff. I assume you made a deliberate decision not to do that. Can you say something about why you thought?
So I mean, so in this case, oh yeah, sorry. So that's a good question. And in this case, you know, finite state machines and behavior trees are sort of are interchangeable.
Right.
But we just made the decision to go with finite state machines because visually it was sort of easier for, like, we started out and we were like, well, these things cycle, right? And so visually, you know, we had these like cycling behaviors. Finite state machines were really easy to visualize on paper to capture those kinds of cycles. But that's definitely something that we're exploring, right? Like, because we just picked this particular representation, but we hadn't really explored other representations as well. But we know that, you know, behavior trees are another option. Look at that.
Yeah, because if you go with the behavior tree, then, you know, for your on the generation side, you know, everything's already expression-like. The operators over the trees are semantically meaningful.
Yes.
You know.
Okay, but yes, I'd love to talk to you about this because this is something definitely we thought about. I don't know who was first. Okay.
Cool. So this is awesome work. Bosses are kind of cool in fact, they, as you talk about, are kind of like these bits of mechanics that are packaged, and you kind of only deal with them on the boss level. We thought about using finite state machines to model other things like that in games, like crafting systems.
So for unrelated things, we sort of flirted up with the idea of like modeling things like combat and elemental systems, but never sort of in the context of doing this. But, you know, bringing that up, you know, sort of brings back all of those old ideas that we have bubbling to the surface. So yeah, that's definitely something we're thinking about. Thank you. So Albert, did you have a question?
Yeah. So I think a lot of response behavior is some kind of abstraction of like actual behavior. Bosses are, divided into the combination of creators.
Mm-hmm.
So I think you were probably more familiar with me, you know, the project community is constantly researching, trying to, given a model or a skeleton of the thing, try to make natural behavior for that thing. Right?
Mm-hmm.
So I sort of see it connected there. Just to, given this skeleton of this boss, trying to fit natural moving pattern to the side, so that not only it looks natural, but also it has some, it's fun and interactive.
Yeah, so originally when we started this out, we were thinking like fully articulated rigid body kind of structures, and there's been a lot of work generating stuff like that. It's also been shown for things like just mass spring particle systems. If you just add vibrations to like simple linkages, you can get really, really cool behavior. So there's this project a couple years ago called Soda Play, where it's basically like build these little autonomous creatures that like bounce around by just adding vibrations to the springs on them. And you can get some really cool, almost natural looking behavior like that. Here we're just using a very simple kinematic 2D physics system, but there's no reason that we couldn't rip that out and replace it with something, you know, a little bit more complicated with like actual, you know, forces and that kind of thing to try and get some more natural motion out of it. Yes. Sorry, in the blue.
So something I've been noticing more and more in especially RPG type games is that if you go through a dungeon and one enemy will have like a certain mechanic, and another enemy will have another mechanic, and then the boss will have all those mechanics.
Yes.
So like the progression is showing you the different mechanics, so then when you get them all, you know what's going to happen.
Yes.
And I think this system is really cool because you could trivially make those sub NPCs out of the boss NPC, right? Because you have your graph already. So I think just limiting yourself to bossing numbers might be selling yourself short. I think this is a really good way to generate these sorts of dungeons where you had boss mechanics already thought up, and then maybe you could generate NPCs that are sub-bosses in some way.
That's actually a really good idea, because you basically take these graphs apart and repurpose them. I mean, progression is something that we've thought about. Obviously, in this case, you know, their attack mechanics are super simple, but there's no reason that we couldn't sort of like, you know, expand it to different, you know, there's a session of damage and stuff, and it's pretty extensible. So yeah, that would be really, really cool. That's a very good insight. Thank you for sort of like ripping out, like creating sub enemies out of the actual bosses. Yes.
This is maybe less of a question, comment, but so like, sorry, I apologize for that. Like, so Moldorm is great because like, right, he's a worm, right?
Yeah.
We know that we see the following. That's great. And like you said, one of the things like you're like that's like really fun is like the like whack-a-mole one. Like I think a lot of these like the boss things, it's like sort of really opposite. It's like they have some sort of like other meaning to them. It's like, oh well, yeah, we see the behavior, and oh that's worm-like, or oh this one was whack-a-mole. I think a key challenge will be like finding the like not just playable ones and not just like running an agent through it and seeing it like, but ones that are actually like evocative and meaningful to the player.
Yeah.
I don't know, do you have the insight on how to do that?
I mean, so
turn it into a question?
no, I mean, like, so that's definitely something we're thinking about. It's not sort of it's not really within the scope of this particular model because we're not considering sort of like narrative significance for these kinds of things. But like one thing that we sort of envisioned is a game where people just fight these, right? And so of these, we sort of pick out like, bosses that people seem to like, and we can study, based on how they're playing them and like what they say about them, what kinds of things do they represent, and sort of like imagining it's like, oh, give us feedback about this boss you fought, and it's like looking at that feedback and seeing if we can sort of like start ascribing like what they talk about in the boss to like the things that we're generating, and then sort of start trying to generate like what these bosses are about, or little stories about the bosses based on what people have said about similar bosses in the past. You were first.
You mentioned towards the end that you're really interested in bosses that kind of adapt their behavior to the player. I was curious if you thought at all that the choice of using state machines under the hood would be limiting at all in types of behaviors you could get from the bosses because they don't have any memory to remember what the player has been doing. Do you think state machines would be good enough?
So the way that we handle things like that right now is that we just create a bunch of, so when we create those components, we generate a bunch of declarations. So we just create like numbers and values that can use to be stored, that can be used to store information. And so this is one place where using something like a behavior tree might be a little bit better because we can you keep track of this kind of information a little bit more easily. But yeah, but right now the way you might represent a boss that has memory, it's like keep around a counter of like how many times something has happened, or like, and then sort of increment that and then use that to transition to new states in the graph based on that. And that would be one way to do it here with this particular model. Yes.
Following up a little bit on Adam's question, I know you mentioned that you have Moldorm here. You also said you had like a description of Dracula in the paper.
Yes.
How many? How much work have you done in like classifying the pre-existing space of like bosses in video games? And are there like distinct groups or styles that these different bosses fall into, or?
So there's and that's a good question. There's been a lot of work. People have sort of done like informal design, like taxonomies of the different kinds of bosses and their similarities. So it's like some bosses are like very clearly giant set pieces, or others are like actual entities that are like player sized. And we can, everybody sort of has their own different taxonomy for this. And when we set out to do this work, we initially explored and like talked with a designer who had been designing for a game that involved just a ton of bosses. And we're like, hey, what kinds of things can you express in our system? And that sort of helped us to figure out like what kinds of behaviors and edges we were exposing. But yeah, as far as like classifying bosses, that's like a really good question. It's like, are there, in this entire boss space, are there clusters of bosses on certain similarity metrics? And like, should we be exploring those? And I think, yes, that'd be a good place to start seeding like your generation, for example. Yeah. But yeah, if you have any ideas about boss classification, I'd love to talk to you too. So, yeah. Are we okay on time, or?
I think we're kind of done on time. So
okay.
You guys can,
I'm totally happy to talk to anyone if anyone has any other questions. So yeah, thank you very much for having me talk.
So at that, we're going on to lunch. Try and get back a little bit before 2. The recommendation was head out to try and find some restaurants in the area. I know there's also a bar, like pub, cafe